This video is on infrared spectroscopy. So, infrared spectroscopy helps you to identify the functional groups in organic molecules. The way it works is by a beam of infrared radiation passing through a sample of a chemical. There's a diagram down here. It looks rather complex. You do not need to know how it works, but I've just put this so you sort of have a basic understanding of what we're doing. So what happens is you put your sample here, okay, and infrared light is generated and shone through the sample. And what happens is the sample contains bonds, and those bonds, they absorb some of the infrared radiation. So they absorb some of it, but some of it they let through. So the stuff they let through carries on through here, goes through all this, don't worry about what that is, and hits the detector. And this is the important bit you need to understand, is about reading these graphs. So you can see, you get these sort of upside down graphs. You get the peaks, but they're upside down. So the peaks represent points where there is no infrared. So this peak here represents a point where infrared has been absorbed by the sample. And here again, this is where some infrared radiation has been absorbed by the sample. You have a reference cell so you can compare it to just the solvent alone, whereas this would be the solvent plus the sample you want to test. So throughout this video, you'll need data from the data sheet that you get given in the exam. So here is a photo of the data sheet that you'll be given in the exam for infrared absorptions. So you can see you've got different bonds. So you've got an NH bond, OH bond, CH bond, another OH bond. See, these guys are in, that's in acids, that's in alcohols, but it's the same bond, just in a different organic compound. And you can see each of them has their own specific wave number measured in cm to the minus 1, which is the wave number of the infrared energy that they absorb. So you can see the carbon-carbon bond absorbs energy between these wave numbers, whereas NH bond between these wave numbers. So it would be really good if you had this handy printed out for the next part of this video so you can refer to this data as we go on. So in the exam you might be given a spectrum that looks something like this and be asked to figure out what it is, or be able to identify, to explain why is this ethanol. This is ethanol, but why? So what you'll do is you'll look at your data sheet and you'll see that there's this absorption peak here. And this absorption peak, you can see it's in this range of wave numbers here. So this tells us that it must be an OH bond. And specifically it tells us, because it's in this between these wave numbers, that it must be OH in an alcohol and not OH in an acid. You can see this absorption peak. You always see an absorption peak around here for organic molecules, or most organic molecules, because most organic molecules contain a carbon-hydrogen bond. So this is for the carbon-hydrogen bond. And over here, anything sort of below 1,500, you don't really have to worry about this. This is something called the fingerprint region. We'll talk about more about that in a second. So this is another question you might be expected to do something like this. So you've got two spectra, and which of them shows the aldehyde and which one shows the carboxylic acid? Well, you should know that the aldehyde is just containing a C double bond O, whereas the carboxylic acid also contains a C double bond O, but it also contains an OH. So look on your data sheet. Where should there be an OH? Well, you can see there's definitely no OH here. So an OH is always this broad, deep absorption peak around this sort of wave number. If you look at this one, this one does have a broad peak around this correct wave number. So that tells us that this must be the carboxylic acid and this must be our aldehyde. So you can see they also both have these quite deep, thin absorption peaks here. So this one, due to the C double bond O, and this one, and this is also due to the C double bond O. So both of them must have C double bond O. But this is the point which tells you that this is the carboxylic acid. So I mentioned that anything below 1,500 cm to the minus 1 is called the fingerprint region. So this is the spectrum that is unique for every compound, and so it can be used as a fingerprint. So all you need to know is you need to know the definition that it's unique for every compound, and it can be used to identify a compound or check if a compound is pure or not. So if a compound has impurities, it will have a different fingerprint region to a pure sample. So if you have a sort of database with thousands and thousands of pure samples, you can compare your maybe unknown sample to find out, is it pure, is it the sample, is it the same compound? That's all you really need to know about the fingerprint region. Other than that, unless they ask a question about defining it, just ignore it when you're trying to interpret spectra. Okay, so we're going to look at some different examples. So these are all alcohols. You can see they all have this broad, deep peak in the wave number of around 330. What you need to be able to identify is you're given the wave number for alcohols, so 3230 to 3550, but what you're not told on the data sheet is the sort of shape of it. So you can see it's quite wide, we use the word broad, and it's quite deep. Opposed to, if you think about the NH, if you look at your data sheet for NH is actually in the same wave number, the same sort of range, but NH is much, much shorter, doesn't go down so deep. Again, you can see here you've got your CH, CH, CH bond. If you look at the acids, so the acids are quite similar. They've also got this broad, deep peak for the OH, but can you see it's shifted to the right? If you flick back in the video, you can see that the alcohols are slightly to the left. Also, the acids, you can see all of the acids, the OH peak, absorption peak, joins up with the CH peak. So you get this very, very distinctive shape. So you should just be able to spot, in an exam, you should just see this shape and instantly, right, barely any thought, be like, that's the acid. So these diagrams show C double bond O. So that's C double bond O. What do you think that is? What is that? Is that going to be, is that an OH and an alcohol or an acid? Hopefully you can spot straight away that's an acid because it's joined up with the CH. So over here you've just got C double bond O. Oh, there's the acid. You can see it's an acid, so that's propanoic acid. This one, you can see C double bond O here. And again, you can see the C double bond O. So the C double bond O is, you can see in all these examples, it's quite thin, quite sharp, and it's very deep. If you look at your data, you'll see that there's one which often gets confused with the C double bond O, which is the C double bond C. But we're going to look at an example now and see how they're different. So all these examples show the C double bond C. So you see the C double bond C looks very similar. It's also sharp. It's also a very similar wave number. The difference is it never really gets that close to the bottom. It's much higher up. In this example here, it's really high up. So you can see the C double bond C can be as short as this or go down as far as this, but it's nowhere near as deep as the C double bond O. So this is just a little graph showing all the different ones you need to know about. You can see you've got your C double bond C, C double bond O, but the C double bond O goes deeper and is slightly to the left. You've got your OH, your NH, so you can see those both conflict. OH and NH have the same range, but NH is a lot shorter. You can see your C triple bond N and your CH. Okay, so have a go at this question. You can see in this question you've got a spectra. You're told it could be either ethanol, ethane, or ethanoic acid. So pause the video, have a go. So hopefully you worked out that it was ethanol because you can see that it can't be ethanoic acid. If it was ethanoic acid, these would be joined up. And it also can't be ethane. If it wasn't ethane, there would be no absorption peaks here at all. There would be this one, but there wouldn't be this one at all. In a question, when you're asked to explain why something is something or why something isn't something, you need to always include the bonds. You say, for example, if the question said, why is this not ethane? You would say, this cannot be ethane because it has a broad, deep absorption peak between the wave numbers 3,230 to 3,350, indicating the presence of an OH bond in an alcohol. That's how you answer that question. You need to include the wave number and the specific bond. Okay, again, try this question, pause the video. So is this butanol, butane, or butanal? So hopefully you worked out that it was butane, because if it was butanal, you'd have this deep peak here for the C double bond O. If it was butanol, you'd have this broad, deep peak for the OH. So again, pause the video, guys, try this question. Is it one of these three? This one must be propanone because it's got this deep, sharp peak for the C double bond O. It can't be the alcohol because the alcohol would have a broad, deep peak for the OH. It can't be the methyl, I think it was methyl propane, was it? Because that wouldn't have this sharp, deep peak for the C double bond O. So just to give you an idea of how the examiners like these questions answered, here's a real exam question. So this one says, identify one feature of this infrared spectrum of pure sample of X that may be used to confirm that X is an alcohol. So they've told you it's an alcohol, how can you confirm that? Use your data sheet. So you have to answer it exactly like this. So pause the video, try it yourself, but this is the answer coming up. So you have to say, absorption peak in the range of 3230 to 3550. See how it's underlined? So if you didn't include the wave number, the range, you could not get the mark, even if the rest were perfect. Okay, the only other way you get the mark is if you give it a specified value in this range, or mark correctly on the spectrum. So the following slides, we've got 5 different examples. They can be propanoic acid, butanone, 2-methylbutyrene, 1-hydroxypropanone, or bute and 2-ol. You may not have come across the term hydroxy. You won't really be asked to name stuff with hydroxy until A2. Hydroxy just means, it's actually the same as if it ends in OL. So hydroxy just means there's an OH group. Don't worry too much about that just yet, but just that 1-hydroxypropanone contains propanone group, so the C double bond O, and also an OH group, like an alcohol group. So have a look at this one here, pause the video, see if you can identify which one of these things it is. Hopefully you've spotted that it's got an OH group, so that means it's either propanoic acid, hydroxypropanone, or butan 2-ol, so it can't be these two. It's also got this deep peak here indicating the presence of a C double bond O, which tells us it can't be butanol, because that wouldn't have it. So it's between hydroxypropanone and propanoic acid. So both of these would have a similar spectra. It's propanoic acid because the OH is joined up to the CH bond here. Also, the OH for acids is slightly to the right. So if you look at its wave number for the acid, it's shifted to the right. If it was an alcohol, it would be more to the left. So pause the video and have a go at this one. So looking at this one, we've got definitely an OH. We've got no C double bond O, so can't be propanoic acid, can't be butanone, that doesn't have an OH, can't be this, because that would have a double bond C, so it leads us, must be butanol. So pause the video. So this one, no OH, so can't be that, can't be that, can't be that. So we're down to these two, butanone or 2-methylbutene. Okay, so we've got this deep sharp peak here, but is that C double bond C or C double bond O? Well, hopefully you remember that C double bond O is the really deep one, so this must be butanone, not butene. Okay, so pause the video, try this one. So in this one we've got an OH, we've also got a C double bond O. You can see that because the CH bond and the OH bond are not joined together, this can't be an acid. So it's got an OH and a C double bond O. The only one we know that has that is the hydroxypropanone, so this must be hydroxypropanone. So again, pause the video and try this one. Okay, so, well, you might have, by a process of elimination, you may have worked this one out. But if you look at it, it's got no OH bond, it's got no C double bond C, no C double bond O, so it can't be that, can't be that. Can't be this one, or can't be this one, so it must be the 2-methylbutyrene. You might be thinking, where is the C double bond C? Well, it's actually this bit here. That is our C double bond C. So sometimes C double bond C peak is really, really small. So this is our 2-methylbutyrene.